So thank you very much for this. Great honor to be here. So thank you very much for inviting me to give this keynote presentation. And I have to say it's a fantastic conference, and I have seen a lot of fantastic things. So really great to be here. I'm from the Center for Advanced Robotics at Queen Mary. And I have been working in soft robotics maybe 8-9 years. And it started with a project called StiffRob, and that was of course very much influenced by the collaboration I had with SSSA in Italy. And at the time I was totally new to the idea of taking an octopus and using it as a role model for soft robotics, while Cecilia Lasky was already working on her octopus project that was already in full swing. And StiffRob really gained a lot from that project. And so I would very strongly argue that because of Cecilia Lasky, I'm doing now soft robotics, and I'm very happy about that. And so today I have been asked to see how perception or sensing can be linked with this kind of new area of soft robotics. And so I want to try to give an overview, but I feel it's difficult because now I have been attending this conference and I have seen so many sensing approaches, and it's really difficult to give an overview there. I suppose everyone here agrees that soft robotics has a paradigm shift, and it really influences us, our way of looking at robotics. So I suppose, maybe not you guys, but many working in robotics, the public, sees this as the kind of normal robot, the traditional one that we are used to, so really made from very stiff components. And there's really now a trend to get away from there and maybe create something more like that, to embrace something like that, that can be used, for example, as in this example, for interaction with humans. So there have been many advances in robotics, and I want to show just a few. So now the sound is in the way. I interrupted. Yeah, I was told that's the only way to switch off the sound. Let's do that again. Okay, that's better. So different systems are developing. So we can see here from Harvard, from our place, even a company, Soft Robotics, developing now systems. So this shows to me there's a lot of interest in the area, and it's moving forward. However, these devices are so far very much at the beginning, and there is lots of development still needed. So what I see is systems that show it works. It shows that we can create devices that can move. But I think we need to now try to step a bit further and see whether we can equip those devices with the right perception so that they can also carry out meaningful tasks. Here is another example, and I'm contradicting myself here a bit. So this was created in collaboration with colleagues from Poland, a research organization called PIAP, and here we have a soft robotic device that is made of silicone rubber material, and it has chambers inside that can be inflated, and similarly we have a gripper attached at the end that can actually carry out a task. The interesting thing is there are no sensors in there, and still the system was running for many days without any problem. Obviously it was programmed to start with, but once it's programmed, it had the capability to, let's say, generalize about its task and was able to pick up the ball even though it was not always arriving at the same point. But as I said, we need now to see whether we can move forward to some more intelligent and autonomous systems, and those need really something to perceive the environment so that they can carry out some tasks. So where have we been beforehand? Yeah? So here is an example of a robotic manipulator, and we can see on the left-hand side the kind of sensors that we're all used to, and they are all made of rigid components. And it is very easy now to equip a system that is already made of very rigid components, as we can see here, with those rigid type of sensors. You just screw them on and then off you go. However, the challenge will come if you look at the soft robotic systems. So the approach taken so far in the rigid component robots is to create an inverse kinematics model, and then you need to only specify points in space, and the rest is just then a path planning problem. So that is very straightforward, and here we can see it in a summary. So we sense the environment, we do some calculation, and then we send commands to the actuators, and in most cases, if we have a rigid component robot, we will reach our target. However, if you think about it, the traditional robot arm in particular can be used to actually measure the environment. It is actually a measuring tool. So I'm demonstrating this now here in those images, where I use a so-called Zollstock, which is a German word for a measuring stick. And you can point now at the environment. You could do this with your robot arm and actually measure distances, measure positions, find out where obstacles are in that environment. It's like, as you can see, I can hold it against certain points in space and can measure the distance. Maybe sometimes I have to go around a bend, but it shouldn't be a problem in a robotic device that can also measure the angular position. And I think that is neglected in rigid component robotics. So the models sometimes fail, and so maybe there is also for rigid component robotics a possibility maybe to embrace that. Although on the other hand, we might think, a big KUKA robot arm suddenly moving around in space to measure it might be not the best idea. However, I see there's a lot of potential for soft robotics. And as Daniela Russ also said at the end of her lecture, active exploration using sensors built into the soft robotic devices to understand the environment. However, what can we do now? If we have a soft robot, there are quite a number of challenges, because we have these flexible devices with their infinite degrees of freedom, and we have also quite a lot of sensor placement problems. We have seen the traditional sensors are not really made for soft robotics. We need to think about miniaturization. We have to distribute these sensors if we want to determine, for example, the pose of a soft robot. The rigid sensor should not impact too much on our soft robot. And the last point, I think, is also becoming more and more important. I think there is more and more also an interest in bringing robots close to humans. And for this human-robot interaction, I think soft robots are ideal. So here is really an area we can move into, and these challenges have to be overcome to make meaningful robots to operate in complex and difficult environments. So if you look at the different sensing requirements, so we have on the one hand the rigid component robots and the sensors that are used in that area, and then on the other hand we have the soft counterparts. So we are talking about strain sensors, bending sensors, torque sensors that have to be integrated, but also proprioceptive sensors that could be built into our soft robots. So I tried very much to kind of classify it a bit, but I think I failed miserably. So I have here an overview. Well, I think I'm missing quite a lot. I can only repeat. I saw many sensing technologies, sensing approaches presented during the conference, and so there's definitely more. And if I don't mention yours, your work is also fantastic. Anyway, so we have resistive systems, flexible, stretchable devices that can be integrated without impacting too much on the softness of our robot. We have triboelectric systems. Capacitive is an area that has developed quite a bit. I've seen also magnetic systems and piezoelectric. So I go through now some examples. So we have embedded resistive strain sensors. These can be used to estimate pose. So here's an example by Yeo and others. And so we can see now a flexible strain sensor is embedded into the structure, and in this particular case it's just a single sensor signal that we can get back. So we need some kind of model to actually relate now the output to the movement of our robotic finger in this case. Here's work by Becke and others. And this is actually now a 3-axis force sensor integrated in a very, very thin device or sensing element. And so 4 capacitive elements are put together to actually do measurements in along 3 axes. I also would like to mention Oliver's work, Oliver Pork. He has already talked about it yesterday. So again, trying now to come up with clever ideas on sensing information about the robotic device, this soft device, without impacting on this softness and this dexterity that is so inherent with them. So here we have a microphone and a sound generator integrated. And by doing that in a clever way and processing the data, I can actually identify where the finger is in contact with the environment. E-gain-based sensors have been developed for quite some time now, and I would like to mention here Yonglei Park and Robert Wood working on that sensor. And again, you can see with this kind of material, we create sensors that are very thin, very flexible, very integratable into robotic devices. Another area, also a number of people have worked on it. I show here work by Shepard. And so these are flexible tubes that are filled with a liquid, and we can use them now to actually measure the bending or the shape of these robotic fingers of the robotic hand we can see in this particular example. One issue one should highlight very much, and I haven't really spent too much time on that, but position and force are very much coupled in these soft robotic devices. So we need to, it is not sufficient just to add those sensors and then to start measuring. We have to also have some software behind it to make sense of what we are measuring. And often it is difficult to distinguish between strain and forces. So there are challenges we need to keep in mind. So I mentioned already stiff lock earlier, so just come back a bit on to show you a bit of the work that we have been doing. So we have been developing this soft robotic device. Usually I show an octopus in my presentation, but today I don't. So we try to take inspiration from biology and create now these soft robotic devices that can be used in minimally invasive surgery. This is a silicone rubber system with a camera integrated, and the camera images are fed back to the user. So this system has no sensors apart from the camera at the tip, but we also looked very much into integrating sensors with our soft robotic devices as part of this project. So here we are looking at a fiber optics based approach. So we have fiber optics that run through the system here, and we measure now the distance between the fiber tip and a light source. And that is changing when we stretch it or when we bend the device, and we can then use that information in addition to some processing. In this case, we use a constant curvature model, and we can then present, visualize the movement of our system. So we have a pose sensor here. Here in collaboration with Ritsu-Miken University, Shinichi Hirai is here, we have developed this mock-up of a soft robotic finger, and this was, I think, very interesting work we have done there. So we used an electroconductive yarn that was integrated here. Actually, we're using 3 of them, and again measuring now how this yarn was changing its resistance. We could actually calculate in which direction our little robot finger was pointing. We were also looking into developing force sensors for our stiff lock manipulator, and here you can see a system again based on fiber optic measurements, and we have these, here's the mouse. We have these sensing elements, so these are deformable structures that allow us to measure forces along 3 axes. They are rigid. So we try to avoid now putting them at the tip, so they are sitting here on the base. Yeah? So here the sensor is at the base. We apply our forces at the soft end and try to measure through the structure. Obviously, that requires some modeling of that structure so that we can make sense of the forces that are applied at the tip and then transferred to this soft system. So I've seen very interesting work on morphological computation, for example. Lots of work has been done also on deep learning. So I think there's a lot of potential there to improve the sensor output. We have also looked into tactile sensors. So again, trying to make use of our technique that we're using, the fiber optics, and you can see here are 2 fibers shining into this dome-like structure, and when there is a force applied on the outside, we can measure that. So the interesting thing here was to try to be as compatible with the softness of our system, and so that was these tactile elements were integrated in a elastic sleeve on top of our robotic device, and it was not impacting on the dexterity and softness of the system. So it could stretch still and bend, as we can see here. Another approach we also looked into, so we tried to really explore different ways of using fiber optics. So in this particular case, we are actually bending the fiber. So the term is macro bending. So we are looking at integrating our optic fiber, one optic fiber strand just going in and coming out, LED shining light on E, and then a signal coming back by changing now the orientation and the position of that these fiber rings that form, or these loops, I should say. We can actually measure extension. Integrating that now with a cylindrical structure like this, we need 3 of those, and again we can measure the pose of our robotic device. So I go to a big case study here. So we have developed something that we call variable stiffness links, and so these look very much like very normal links, so they're at the moment inflated, and the idea is to equip standard robot arms, but really do something more clever about the link than is normally done. A link is just a link. But here we have now links that can actually change their stiffness, and when you let the air out, you reduce the pressure, we have a system that becomes very soft. So very useful for human-robot interaction, because now we can stiffen it when required for payload lifting, for example, but can also reduce the pressure when needed, i.e. if a human is in the vicinity. And so here we found that we have already a sensor built in, because we are using a pressure regulator. So the pressure regulator, pressure sensor, sitting at the base of this robotic device was needed to keep the pressure constant, but we could also read a bit further, and if you look closely, then you see some spikes which are amplified here, and these amplified happen when there is a collision with the environment. And we could actually distinguish between a collision more at the tip and more at the middle. So here you see the collision, and in this particular program, the collision occurs, we detect it, and we can move away from it. Now, extending from this idea of having a fabric-based link, we continued our work again with the Macon University and have created or very much our colleagues Shinji Hirai and his team have developed this conductive fabric-based robotic skin, which can be very nicely integrated into our fabric-based robotic device and can be used to measure proximity to obstacles and also contact. And that will be actually published in a RAL paper and in ICRA in Montreal. But what about scalability? So we are also looking into how can we possibly simplify the process, how can we possibly use sensors that are more scalable than what I have shown so far. Sensors I've shown so far are more single sensors. And maybe one day we will manage to get so far and create robotic devices that have manipulation capabilities, like shown here by this expert with his stick. But for that we need to really have highly distributed sensors. So trying to now take inspiration from humans who have lots of receptors in their fingers, in their fingertips, and obviously that is not only a sensing question, but it's also about neural processing, about estimating and understanding the signals that come, and create some clever commands out of it. So I bring this slide up here as well, because I think vision is really happening, and is already used also in the robotics community. But I think we should really embrace it, and I say that even though I'm not really a fan of deep tech, deep learning and deep neural networks, but I see it as something that is happening and is working, and so maybe it could be also used as a tool in robotics, in particular in soft robotics, to learn models of robotic structures. And also it could be possibly used as a sensor that is part of a tactile sensor, as we, for example, do at Queen Mary, so where we integrate sensing structures that are based on flexible material, and one of my PhD students was presenting it earlier today in the poster session. So we have a camera there that observes pixels that are moving when contact is occurring with the environment. In our case, we try now to use just one vision sensor and to measure not only the tactile information, but also the force information. Obviously, I have to mention in this context work that is happening at the Bristol Robotics Lab, the tactic work, which operates on a similar principle. But I've also seen this robotic system, or this system to sense now deformation. Here the system starts bending, and the color that is observed by a camera is changing during the bending process, and again that can be interpreted then as the amount of bending occurring in this robotic finger or arm. Okay, I go quickly again through a few of our applications of our optical fiber-based approach. We have done quite a lot there in this area. So we have integrated it with fingers of robotic hands, and so these are fairly rigid, but I think there is also a lot of scope to bring that technology to softer devices. We have extended this idea also to proximity sensing. I think that is very useful in any robotic device, but also for soft robotics. And we can measure now the proximity to obstacles. And if we combine it in a clever way, we can, with the force sensors that are also integrated, we can even measure the stiffness of the objects that we are handling. Good. I'm coming to my conclusions. So at the moment, a lot of stuff is happening, and again, I'm very grateful to be here and see all this fantastic work happening. But I think we are still at the beginning, and so much more, I think, will happen. I think work should focus on now seeing how we can bring sensors on board, how can we integrate sensors into these soft robotic devices. It is happening already, but still very challenging, and more work needs to be done. So there's opportunity to make use of structural elements for sensing and actuation, and vice versa. The decoupling is definitely a challenge. So if you look at force and pose estimation, and also, as I mentioned already, scalable sensor systems are probably also needed. I would like to thank my collaborators. Unfortunately, I have the old slide here, so some of them are missing. I don't know, I couldn't find it anymore. But without those, it would not have been possible. And I want to thank especially those three who are here this time and helped with the preparation of my presentation today. Thank you very much.
25 minutes is very short for your keynote, and so we accept only one quick question here. And after the banquet, so at the banquet you can.
Of course.
Is there any question? Oh, over there.
Yep.
Thank you very much for your presentation. And could you comment on, could you give some insight on your opinion about which kind of technology or approach you think is more powerful, has more potential in terms of, applications of robotics in order to reduce the part of the computation? Because actually the hardware part, I think, as you said, there is a lot already ongoing, right? For soft robotics. I mean, there are a lot of different technologies ongoing, and these will be optimized more and more in the materials, etc. But especially for gathering distributed information, as I have seen you are doing with different kinds of approaches, could you comment on your opinion?
I suppose you asked me possibly the most difficult question.
Some comments.
So what I haven't spoken about is the environment, and Oliver is here, so he has a whole project on that. So I think the environment is also very important, and so that would mean that we probably will not be able to create a robotic device that can solve all problems. So it will be very application oriented, and we need to also consider the environment, the interaction with the environment. The physical interaction is so important. After all, we make robots to get in contact with something. So that, I think, will be definitely, let's call it a constraint that one has to keep in mind. Now, to now move forward towards creating robotic devices that have maybe more intelligence embodied within their structure. Very difficult, so I could assume simulations would help. So creating good models, maybe again. I mean, that different modeling technologies that can be used. So to see whether we can find optimization techniques where we model the whole structure and also the interaction with the environments to answer your question. So to see what is optimal for a particular task, and then hopefully by creating these devices to reduce the computational burden. But I think I have to be pretty vague about it. Yeah, it's definitely a very difficult question. It needs more work. Maybe also we could see the work that is happening in parallel, and hopefully gather the information everyone gains to help us then to converge to something that is more efficient in a computational sense.
Okay, so thank you again.
Thank you.